Hello again, another recording, this time again still on differentiation. So we're going to have a look at some more examples, just diving a bit more in depth into the process of differentiating functions, finding the gradient at any particular point. So let's have a look at the quintessential warm-up questions. So 4 questions to have a go at. So pause the video if you've not got these in front of you, copy down the questions and attempt them. When you're ready to see the answers, press play and we'll go through them together. So let's have a look through them now. So question 1, I've got this curve, y equals x squared minus 6x plus 10. Find dy by dx. So all it means by dy by dx is just the gradient function. So like we saw earlier, all we do for each term piecemeal, each term individually, we take the power of a variable, in this case x, which we're differentiating with respect to. We bring the power to the front, multiply by any coefficient at the beginning, and then we just drop the power by 1. So x squared becomes x to the power 1. The 6x, the 1 power here just goes to the front. 6 times 1 just becomes 6. Then we have x to the power 0. So the quick way of doing it is just to notice that the x just disappears and you're left with just the 6. The constant term vanishes, so we just have dy by dx equals 2x minus 6. Part B, find the x-coordinate where the gradient of c is equal to 0. So this is the gradient function, and so we just want this dy by dx, the derivative, to equal 0. And so we just set 2x minus 6 equal to 0. Rearrange and solve. Therefore, you'll hopefully see that x is equal to 3. And part C, hence find the y-coordinate on the curve C where the gradient of c is equal to 0. We're just going to substitute in x equals 3 into this function here. And so y, when x is 3, is going to be 3 squared minus 6 lots of 3 plus 10, which is going to be 9 minus 18 plus 10, and so y will just be 1. In other words, the coordinate of the point on the curve with gradient 0 is going to be 0, 1. Question 2, the same curve. Now we're going to rewrite this in completed square form. So we've got to write it as y equals x plus a all squared plus b. So to do this, we just need to remember how to complete the square. So we put the x squared as an x in the bracket. We half the coefficient of the x term, so minus 3. We then square that. We then subtract off this constant term squared, so subtract off minus 9, and then just plus 10. And so that will give us x minus 3 all squared, and the minus 9 plus 10 becomes plus 1. So therefore we should have y equals x minus 3 squared plus 1. So our a is minus 3 and b is 1. So for part B, we're going to use this to write down the coordinates of the minimum point of C. Well, this is going to be a minimum when the thing in brackets, the squared term, is equal to 0. The lowest value something squared can be is 0 when the brackets are equal to 0. So the minimum point is going to be when x is 3. That gives us 0 squared plus 1. So the minimum will be 3 and 1. So to just try and link in to how the derivative actually relates to the curve, if I show you the actual curve here, taken from Desmos, that's the actual curve we have. So we've got a minimum at 3 and 1, which is where the gradient is 0, where we use the derivative to see that. And so where the derivative is 0, that will relate to either a minimum or maximum of a quadratic curve. In this case, it's a minimum. Question 3, we need to rewrite these as expressions in the form x to the power a plus x to the power b. So for part A, x squared divided by x is x squared. and x squared divided by x just leaves us with x. For part B, same idea. X to the power 5 divided by x to the power 6 becomes x to the power minus 1. This term here, the new power of x will be minus 2 minus a further 6. That becomes minus 8. And lastly, what I'd suggest we do first of all is to rewrite the denominator as something a bit more manageable. And so x squared cube rooted is x to the power 2/3. The cube root is to the power 1/3. So something squared to the power 1/3, power of a power, we multiply the 2 and the 1/3 to give us 2/3. So now, just subtracting 2/3 from each of these powers at the top gives us, here we have x to the power minus 1 minus 2/3, which is x to the power minus 5/3. And the second term here, minus 2 minus a further 2/3, that gives us minus 8/3, like so. And question 4, some binomial expansion work, well, binomial probability distribution rather. So we're told that the variable x follows the binomial probability distribution with 10 trials, the probability of success equal to 0.3. We need to find the probability that the variable takes on values 4 and upwards up to, but not including 7. So the probability that the random variable is 4, 5, 6 or 7. So I'm going to show you a calculator method using the CLASSWIZ. This might be different to what your teachers told you to do, but either way, here's what I've mentioned to do in class. So we need to rewrite this in terms of the probability that x is less than or equal to a value first. Now if x must be less than 7, that's one and the same thing as saying we want x to be up to and including 6. However, if we did that, this is going to include, that's the wrong way around, apologies, so let's undo that line. This is going to include x being 6, 5, 4, 3, 2, 1 and 0. However, if we look here, we only want to include from 6, 5 and 4. We don't want to include 3, 2, 1 or 0. So we want to ignore these probabilities. So if we just have this, we're going to overcount. So from this, we need to then subtract off all the probabilities that are 3 and less. So we need to subtract the probability that the variable is up to and including 3. And so if we do that, we'll just be left with the 6, the 5 and the 4 which we want. Because this has got inequalities in it, we're going to use the binomial CD function, which I'll show you here. So we press menu, we press, show you how to do it. We're going to press 7 for distribution. We're then going to scroll down to binomial CD and press this. Go for variable, option 2. So we want that x is up to and including 6. So set x as 6, number of trials n is 10, probability of success is 0.3. Press equals and we get a probability of 0.9894. Give it to 4 sig figs for now. We can always round down to the usual 3 sig figs after. So 0.9894. Less the probability that x is up to and including 3. And so we just go back to the calculator, just press AC, it will store what we had previously, and just change the x from being 6 to a 3, and we get 0.6496, so minus 0.6496. And so if we just do one, subtract the other, I could do it myself, but just to be safe, why not just use a calculator? So go back to normal mode, press menu 1 and key in 0.9894 subtract 0.6496 and we get 0.3398. So to our usual 3 sig figs we get 0.340. So I've given the figures in the intermediate stages to an extra significant figure just to avoid the chance of any rounding error. Okay, so just to consolidate previous lessons' work, like I was saying from the previous lesson, we can take the derivative by differentiating each term in the function piecemeal, just taking it one function, just one variable at a time. So if we have a look here, we've got this function, which is quite ugly looking because it's got a denominator at the bottom as well. So what we're going to do here is just neaten up this initial function. So let's rewrite it, first of all, as f of x. That's going to be, first of all, x divided by x to the minus 3. When we divide, where the bases are the same, we're going to subtract the powers. And so this new power of x is going to be 1 minus minus 3, 1 plus 3, which is x to the power 4. Next, we're going to have x to the power 4 minus minus 3, which gives us x to the power 7. And then we're going to have minus 1 divided by x to the power minus 3. And so we can consider this, if you like, as x to the power 0. So if we rewrite this if you wanted, remember anything to the power 0 is 1. 0 minus minus 3, we get x to the power 3. So that's going to give us x cubed. So we didn't need the minus 1 in front after all. But now, if we take the derivative of this function, bring the powers to the front, so we get 4x, knock 1 off a power, the 4 becomes 3. The same here, so x to the power 7, the 7 gets brought to the front, the power of x becomes 1 less. And here, once again, bring the power to the front, so the 3 is going to multiply that minus 1 to give us minus 3, and the new power of x is going to be power 2. So that's our derivative of the function. That's part A. So for part B, same idea. What I'd suggest doing is neatening up the bottom bit first. So just leave the top as it is and change the bottom to 4x to the power 3 over 2. Remember, the square root is to the power half, hence this denominator of 2 in the power. So that becomes 4 on the bottom, we're going to have a quarter. The first power of x is going to be x to the power 1 divided by x to the power 3 over 2. So the power is going to be 1 minus 3 over 2, which is going to be minus a half. And then the next term, minus 8 divided by 4, we get minus 2. The new power of x will be 5 subtract 3 over 2. 5 take away 3 over 2 is going to give us 3.5. As a power of x without using decimals, that's going to be 7 over 2. So we can now differentiate this function. So we're going to have dy by dx equals. So this power of minus half comes to the front, so we're going to multiply the quarter by minus a half. So a quarter multiplied by minus a half is going to give us minus 1/8 x. Then this power is going to subtract by 1, so that becomes minus 3 over 2. And over here, that 7 over 2 is going to come to the front as well. So we're going to have minus 2 multiplied by 7 over 2. So that's going to be minus 7 x. And the 7 over 2 we're going to reduce by 1. 7 over 2 subtract 1 is going to be 5 over 2. And for c, here we may as well expand out this to again make it just easier to work with. So the square root of x multiplied by 1 just gives us the square root of x. Square root of x multiplied by minus 2 over x. So that's x to the power half. So we're going to multiply that by 2. So x to the half divided by x to the power 1, that's going to give us x to the power of minus a half. So we're going to have x to the half subtract 2 lots of x to the power of minus a half. So therefore, if we differentiate this, dy by dx, that's going to become half x to the minus half. This minus half will come to the front. Minus 2 times minus a half, minus times a minus gives us a positive. That's going to become positive x to the new power. So subtract 1 from minus a half, we're going to get minus 3 over 2. And that's all of our derivatives for this question 1 done. Question 2, find the gradient of a curve at the point 1/2, where the function of x equals 1 minus the cube root of x to the power 5 plus 1 over 2x. So we need to just rewrite this function slightly neater. So we're going to have fx equals 1 minus x to the power 5 over 3 plus a half x to the power minus 1. So it's really important, as we've seen, to get the function in simple power form, in simple index form, without any surds or roots if we can help it. So therefore, for gradient of a curve, dy by dx, we can differentiate each term in turn. So the constant of 1 will just simply vanish. That will become nothing. This here, we're going to subtract 1 from the power, and we're going to bring this to the front. And so it's a minus x, so we're going to have minus 5 over 3. And the new power of x, that's going to reduce by 1. So 5/3 subtract 1, we're going to be left with 2/3. And over here, the minus 1 is going to be brought to the front, so we're going to have minus a half, because a half multiplied by minus 1 is minus a half. We're going to have x to the power minus 2. So this is f dashed of x, this thing here. So what we want here is to work out the gradient when x is equal to 1. So when x equals 1, f dashed of x, which is dy by dx. I'm just introducing this to let you know that it's one and the same thing. Okay, so by f dashed of x, that's a different way of writing the derivative, which another way is dy by dx. And so we're just going to substitute 1 into this expression here. So we're going to have minus 5/3, 1 to the power 2/3, minus a half times 1 to the minus 2. And so all we're going to have here is minus 5 over 3 minus a half. So again, you could just get these denominators the same, get them all out of 6 and see what we get. Well, don't calculate. I'm going to show you something else on this CLASSWIZ, which is very, very useful. So if I just show you this here, so if I do minus 5 over 3 minus a half, get minus 13 over 6. However, something I've held off from mentioning until now is, could we use the calculator to differentiate functions for us? Well, let's see if I can show you this. So if I just get the calculator here, if you have a look on the calculator button, just below menu we have a d by dx. So this is how we can differentiate functions. So if I press shift and then this integral, which is the next chapter, so shift the integral button, we can work out what the derivative will be for any value of x. And so we want the derivative of our initial function, which is this. Okay, so I'm going to show you. You can type this in without any manipulation and it will do it for you. So 1, then it's going to be minus the cube root, so shift square root, then we're going to have x to the power 5 on the inside. So this is a red x, so we need alpha. So alpha x to the power 5, and then plus 1 over 2 alpha x. So it should look exactly as what we have over here. And then if we toggle over here, we can input what we want x to be where we're evaluating the derivative. And so we want the derivative, d by dx, when x is equal to 1. And so if we toggle along and type in x equal to 1, press equals, we can see that the derivative we receive on the calculator is minus 2.16 recurring. So it might seem that this is a different value to the one we've got here algebraically, but actually, if you think about it, this is the same as minus 2 1/6, but it's been given as a decimal. So that's the same, one and the same as minus 13 over 6. And so it doesn't give you the derivative at any one point in exact form, but it's an exceptionally good and easy way of just verifying your result without using a calculator. So check with and without a calculator if you've got a question like this, and the calculator really comes massively in handy, as you can see here. So yeah, just spot that these are one and the same. If you just look at it, you could fall into the trap of thinking you've made a mistake. So just be careful and think this might be a decimal expression of an exact rational fraction. So time for you all now to have a go at just consolidating these ideas. So if you can move on to page 267 to 268, exercise 12e, and attempt all of the questions there, if you can do, please. And again, please do remember, you can leave me any comments within reason in the comments section. For example, some questions you'd like me to go through together, or you can email me any questions if you are struggling on some in particular and you don't want to leave me a public comment. I can't make any promises that I can go through every single question asked, but again, first come, first serve. So if you are struggling, either email or leave a comment and I'll do my best. So try these questions and I'll be in touch soon. Okay, thank you very much for listening. See you for now.